Basically, the high performance for the filters achieved by improving their out-of-band performance. So my focus will be on out-of-band region of the filter. Here is the outline of my talk. After the brief introduction and state of the art, I will talk about the introduction to the proposed method for spurious suppression, then the advantages of the TM cavity, and then wide spurious-free TM cavity filters for narrow and wideband applications, and then wide stop band SIW filter design using the proposed method. So as we know that there is an increasing demand for more data because of Internet of Things applications. So this will lead us to the 5G network, and use of the satellites are necessary to provide ubiquitous coverage to the end users. So with that, there will be a massive use of space segment. And as we all know that space technologies are expensive, so it brings us some challenges, which are cost reduction, bulkiness of the components, and easy integration. So we need miniaturization and lightweight communication payload. So in satellite transceivers, filters are the bulkiest part. So filters with wide stop band rejection are very important. So this is to avoid the use of low pass filters, and at the end we can achieve cost and volume reduction and lightweight communication payload. So as we know that in classical waveguide filters, a cavity has a resonant mode to generate the filter passband, but a higher order modes generate spurious resonance that degrades the filter out of band performance. So the classical approach is used to remove spurious mode resonance is to avoid their excitation or minimize the couplings to the higher order modes as much as possible. So these configuration based on SIW technology and rectangular waveguide technology uses the principle of the classical approach that avoids the higher order modes excitation or minimize their couplings as much as possible. So this method is compared with the proposed method for higher order mode suppression and improving the out of band performance in filters. So the proposed method is explained here with the help of classical waveguide resonator. So this is the fourth order filter response that corresponds to classical waveguide resonator with all identical coupling values. If we look the electric field distribution inside each resonator that corresponds to each frequency point, F1, F2, F3, and F4. So we can see that all are having same amplitude, but they are having a phase difference of 180 degree. That is when we pass from inline topology to the transversal topology. So in this case, these four resonances can be easily suppressed by minimizing only their central coupling value. This is the response that shows when we minimize the central coupling value to those resonances, they can be very easily suppressed. In this case, F1 cancels F2, F3 cancels F4, and for higher order filters, F5 cancels F6, and so on. So the proposed method is here explained with the help of sixth order filter. In the routing scheme, you can see a cavity has a resonant mode that generates filter passband around 9.5 gigahertz and a spurious mode that generates a parasitic band around 10.5 gigahertz. So the coupling to the spurious modes between adjacent resonators is represented by M, and only the central coupling is represented by MC. So if we apply the classical approach, that is what we saw in the previous slides, all the spurious mode couplings needs to be minimized. However, in the response, we can see that the black curve that corresponds when we minimize all spurious mode coupling. And in this case, spurious appears in this case. However, when we only minimize the central coupling value according to the proposed method, and all other couplings in this case are maximum, so we can get the suppression or cancellation of the resonances up to 25 dB, and we can get much better results when we minimize the central coupling value. So in this talk, I will discuss some filter designs with wide stop band performance using proposed method for narrow and wideband applications. So the TM cavity is a well-known structure. It employs TM modes as the resonating modes. The advantages are their miniaturized and small size and their high quality factor. The disadvantages are their spurious resonance due to higher order modes. And in case of higher order filters, coupling RSs that also produce the resonances that limit the upper stop band performance of such filters. So the objective is to work on spurious resonance to improve out of band performance in TM cavity filters. So here is the example of fourth order TM cavity filter. So as you can see, the resonant mode of the cavity that generates the filter pass band around 9.2 gigahertz. And the higher order modes that generates the spurious parasitic band around 16 gigahertz. There is also an additional parasitic band present around 12 gigahertz that is due to these coupling RSs. So the goal is to improve this out of band performance of the filter. So if we apply the classical approach, that is to avoid the excitation of higher order modes and minimize the spurious coupling values as much as possible. So in case this is what we saw in the beginning from the state of the art. In case of TM filters, this can be done by placing all RSs orthogonal to each other. So by rotating iris 90 degrees, we can see it will get the minimum coupling value to the higher order mode, but fundamental mode coupling is not disturbed in this case. So, but if we apply this method, we can see that the spurious mode resonance, because of very small coupling values to the higher order modes, these resonance is still present. So instead, if we apply the proposed method, so in this case, we first remove the spurious due to coupling RSs, as in the proposed method is based on the principle of the minimization of the central coupling value to higher order modes. However, this also works for to remove spurious due to coupling RSs. That is when we decrease the width of the central iris, which means we are minimizing the central coupling value. In this case, the resonance due to irises, in this case, this iris 2 and iris 4 that produces the resonance. The central iris shift its resonance frequency to higher value, and the other two resonance starts to cancel each other. In this way, we can get the suppression for the iris resonances, and the central iris resonance can be shifted to higher frequency value, which will be shown later around 20 gigahertz. So if we apply the proposed method of the spurious suppression to the TM cavity filters, this is the final result without spuriouses. I will not go into the details because there was a lot of technical details involved to achieve these results. But in principle, if we minimize the central coupling value, we can do this by by rotating the iris 90 degree, and according to the field distribution of the spurious mode, we can get minimum coupling only to the central coupling value for the in this 4-pole TM cavity filter, and all other couplings, for example, coupling to the first and second resonator, the RSs in horizontal position, they are not minimum, instead they are at their maximum position. And we can see we can get the suppression of the spurious resonance due to higher order modes up to 35 dBs, and also we can get the suppression for iris resonance up to 30 dBs. So this is the design 1, and the design 2 shows improvement in terms of the selectivity of the filter. As you can by changing the position of irises, it changes the coupling sign, and we can get the transmission 0 at the upper stop band, and it can improve the selectivity of the filter. So the stop band has been increased from initial design of 12 gigahertz to 20.2 gigahertz in this case. So when we increase the filter order, the spurious level also increases. For example, in case of TM cavity filters, spurious due to coupling irises also increases. We have more number of irises that couple the cavities, and the spurious due to higher order modes also increases, and it is difficult to work on this spurious band of the filters. However, the proposed method work also in case of 6th order filter. In this case, the basic principle is same by minimizing the central coupling value to higher order modes, as we saw in the previous slide. According to the field distribution of the higher order spurious mode, placing iris at this position, it will get minimum coupling to the spurious modes, and all other couplings are maximum in this case with the horizontal irises. And we can see that the stop band has been increased from initial result of 12 gigahertz to up to 20 gigahertz. This is the manufacturing of the proposed 6th order TM cavity filter. The manufacturing is done using the classical milling technique, and you can see the result that shows good agreement between the simulated and my result with the out of band region up to 20-21 gigahertz. So the filters we saw in the previous slides was for narrow band, around 1.3% in case of 4th order filter and 1.5% in case of 6th order filter. The challenges in TM cavities when we increase the fractional bandwidth, because we have coupling iris resonances involved, and in this case when we increase the fractional bandwidth, the coupling iris resonance, because increasing iris size shift the frequency for the iris resonances, and in this case it will get closer to the passband and it will degrade the performance of the filter in terms of the rejection. Also, increasing the central coupling will increase the spurious level due to the higher order modes. So, however, a new technique was applied to improve the fractional bandwidth of the filter by keeping the same spurious suppression level. Here we can see, as compared to the previous results, where the iris resonance was present around 10.5 gigahertz, with the fractional bandwidth of 1.3%, it has been increased to 5%, and also it improves the upper stop band performance of the filter. In this case, the 3D designs of the filters is not reported here because it is not published yet, and it is still under further optimization and investigation. But to show the feasibility of the proposed approach to wider fractional bandwidth, we can get much better result as compared to the previous one, which was 1.3%. Now, in case of 4th order filter, we achieved 5%, and in case of 6th order filter, we achieved fractional bandwidth of 4.7%. So in order to show the feasibility of the proposed approach, it was also applied to substrate integrated waveguide technology, as we know that it has some advantages as compared to microstrip technology. It has low cost, lightweight advantage of microstrip and high quality factor advantage of metallic waveguide technology. So here the classical SIW resonator with slots is shown. So with the fundamental mode and with the higher order spurious modes. The objective is to work on these spurious modes of the SIW filter to improve out of band performance in SIW filters. So to apply the classical method, a 4-layer SIW filter has been designed. In this case, when 4 SIW cavities has been coupled using the slots. So if we use the slots at the edge of the cavities, the spurious mode couplings are minimized as much as possible. However, in the response, we can see that because of very small coupling value, spurious resonance appears in this case. Instead, if we apply the proposed method, only the central coupling value is minimum. It means we use the slot only at between the second and third resonator, and we can get the two-layer structure. This is also good for the fabrication purpose. And we can see the spurious mode suppression around up to 20 dBs. The proposed two-layer structure was also manufactured and measured, and the result shows effectiveness in with the simulated result. Of course, in this case, filter size has not been reduced, but yes, we can get the high performance by improving the out-of-band performance for the filter, and we can avoid additional filtering elements in this case to improve the performance of the filter. So in the conclusion, a new method is presented to remove spurious resonances due to higher order modes. Examples of wide stop band TM cavity filter designs of different orders for narrow and wideband applications are presented. The proposed method is general and applicable in case of waveguide TM cavity structures and SIW structures. This is what we saw from the results. Filters with wide stop band performance allows to reduce the cost and to realize lightweight communication payload.